All right, how's it going, everyone? So, in terms of logistics, we have homework 4 is out right now, and I'm going to be releasing the experiments that you guys will. So right now, all that's out is just implementing neural networks, and we'll also have you guys run some experiments on a couple image data sets for image classification, MNIST and CFAR, and that will be out later today. Since the homework was out late, the due date is still going to be on Thursday, but we're going to give everyone 3 extra late days. So you can use them for this homework, or you can use them for, there's only going to be one other homework. So use them as you see fit. And if anyone has any issues because of the homework being out late that the 3 extra days don't help with, let me know, and we'll figure something out. So, do you guys any logistic questions or anything about stuff? Everyone doing good? Yeah. Is there a limit to how many late days? No. That's sort of the point of them. Yeah. So if you want to just use all 7 of your late days on this one, go for it. Yeah, because so I don't think we'll have late days for the project because we have grading constraints, basically. And also for the final project, everyone is presenting on the same day, just during your exam time. Go back to this little thing. Any other questions? Yeah. Yeah, we do. We actually have a thing, so we'll send that out too. I've forgotten to do that, but yeah, I'll send out details about the project. But basically, just anything that is about 2 homeworks-ish worth of work. We'll have some example projects that people can do, but it should be not too much work and sort of a straightforward thing. Yeah. Any other questions? Cool. You don't have a lot of time to do the projects, but we just want people to be able to explore things in computer vision that they're interested in or do something on their own, basically. Cool. So, yeah. The projects can be whatever you want them to be. You will be turning in whatever sort of code you've written, but that's not, most of the grading will be based on basically your poster presentation, sort of talking to you, and we'll have you guys send in your posters to us too, so we can sort of look over them and grade them in case we don't get a chance to talk to you at the poster session. The poster session's 2 hours long, so we'll probably have time to go around, and all the TAs will be there, so we'll have time to talk to everyone and check out what you guys did. But yeah. Cool. All right, so last time we talked a lot about neural networks, and specifically we talked about sort of how we update these neural networks using gradient descent and our backpropagation algorithm, which is just our method of basically calculating these partial derivatives over the neural network. So we talked about this example of basically if we have this 1-layer neural network and we want to basically figure out the weight updates for just this weight v2. The way that we do that is we basically take our loss function and we figure out what the partial derivative is with respect to v2. So we're doing the partial derivative of our loss function with respect to v2. And we can run through sort of this math. And it works out to basically be, we have here sort of the ground truth label y and our model predictions. And we're going to be multiplying that by basically the input that is flowing into v2 from the previous layer. And we can sort of see that here, where basically h1 is h2 is the input that's flowing into the weight v2 as it makes its way to its output. And so our weight update will basically be based on how sort of the distance from what we wanted the output to be versus what the output actually was, multiplied by the input that's going into that weight. And that derivation is entirely just based off of what the derivative is with respect to the loss function. So we're just going to push our weight v2 a little bit in the direction to help minimize this loss. And similarly, if we want to figure out for example, what the weight update should be for W2 in this pretty simple neural network, we're going to run through the same process. where we have our loss function, and we're going to do the partial derivative this time with respect to W2. And when we run through all of the math, we have a similar sort of equation, but we have to sort of backpropagate one step because W2 is further back in the network than V2. So we still have this term, which is basically how far away our prediction was from what we actually wanted to predict. And in this case, we're going to be backpropagating our loss through V1 and taking into account basically the gradient of our activation function, phi prime, and then multiplying it by the input x2. And so we can see that again in this example. We're going to be calculating some error basically at our output. We're going to be backpropagating that error through V1. We're going to backpropagate that through this activation function phi, and then we're going to multiply that by x2 to get our partial derivative for W2. And that's basically what our equation is showing here, getting the partial derivative of our loss with respect to W2. And sort of another way of thinking about this is just based on basically calculating these individual partial derivatives and then multiplying them together so that they cancel. And we can do this sort of for both our weights, V1 or W2. And of course, this generalizes to all of the other weights basically in the same layer, but with different things that you're multiplying by. And sort of the simpler way to think about it is basically as how you would implement it in terms of backpropagation. We're going to calculate some partial derivative at our output, and then when we want to calculate the partial derivative with respect to some weights that connect some layer that we know the input to, or basically, so we know the output of this layer, and we know the partial derivatives of this layer, and if we want to calculate the weight updates for the weights that connect those two neurons, we just multiply the output from this layer, sort of the input to this weight, by the partial derivative at our output, and we get the weight update for just this weight. And if we wanted to calculate basically the weight update for V2 or V3, we would multiply by H2 and H3 by this partial derivative dLdP. And then we can do this backpropagation, which is sort of the important step in neural networks. We've already basically done this before in logistic regression, where we're just multiplying sort of the input by our deltas to figure out what the weight updates are. The backpropagation allows us to backpropagate that error to the previous layer, and in that way we can sort of calculate the weight updates for W instead of just being able to calculate the weight updates for V. So to backpropagate that loss, the first thing we're going to do is basically take our loss at the output and sort of run it backward through this network. So we run it backward through V, and so in this case we're going to be multiplying it by V1 to get our partial derivative here of our loss with respect to H1. But what we really want is our partial derivative of the loss with respect to W1 and W2. So we have to backpropagate it through our activation function phi. And the way we do that is just multiply this term by phi prime of x1 W1 plus x2 W2. So this is just the weighted sum that comes from this layer along these weights. And phi prime will be sort of dependent on whatever your activation function is. So you just multiply phi prime by your partial derivative here to get the partial derivative of your loss with respect to this weighted sum. And then we have the same sort of update step that we were taking in logistic regression. We just multiply basically the input to this layer by the loss at the output to figure out our weight updates for W2. And we can represent this all basically in terms of these matrix multiplications, and this is how you guys will be doing it for your homework. In your homework, you won't be using a bias term. It doesn't matter too much for the stuff we're doing right now, and it just adds on sort of an extra step. But basically, if you want to do forward propagation through a network, we have some input matrix X, and we have some weights W, and you just do the matrix of multiplication of X times W, as long as they're sort of set up in the correct dimensions. We're going to take our activation function phi of this matrix multiplication, and that will apply the activation to every element basically independently in this matrix, because the activation functions usually only apply to sort of each of these individual neurons by themselves. And when we form it in this matrix multiplication paradigm, we can basically batch process multiple examples at the same time. So we have this matrix X, and every row in X is going to be its own data point, and every column in X is sort of a separate feature along that data point. And so we have this weight matrix W, we can just pass in a single row X to W, and we'll get out a single row Z, which will be our output of this layer. Or we can pass in basically multiple rows for X, multiple examples at the same time, and when we do this matrix operation, we will get some number of outputs that will basically be the same number of rows. So X is this matrix. It's an M by K matrix where M is the number of examples and K is the number of features or the number of basically input variables in layer X. We have our weight matrix, which has dimension K by N, where K is the number of features in layer X and N is the number of features in layer Y. And we have our output matrix that we're going to get, which is M by N. So we still have M number of examples, and we have N features per examples, where N is the number of neurons in layer Y. We also have our backward propagation rules. So we basically want to propagate forward through the network. Then we want to calculate some error and backpropagate it through the network to figure out what all of our weight updates will be. And again, we can form this in terms of these matrix operations where we're talking about basically the W's, the deltas at every layer and backpropagating them to the previous layer. So if we have some delta Y that we want to backpropagate to layer X, all we do is take delta Y and matrix multiply it with, this time, the transpose of the weights because we're going backwards instead of forwards. And then we're going to do the element-wise multiplication with this gradient phi prime of the input to layer X. So again, remember, we have to basically backpropagate it both through the weights and also through the activation function. And the order that you do this in, so this is presenting it in one order, basically, where you backpropagate the error and then do the gradient computation right away. In your homework, you're going to be doing it a little bit differently, where you will be given basically the error before it is backpropagated through the activation function. You'll have to calculate the gradient to backpropagate it through the activation function, and then you will backward propagate it through the weights W. But that's all explained in the homework, so you should be able to figure it out. But basically, the point of this is basically we can backward propagate our error using these matrix multiplications as well, which makes implementing it pretty straightforward because all we're kind of doing is multiplying some matrices by each other. And in the same way that we were able to batch process our forward examples, we can batch process this backward propagation as well. So we can calculate basically delta X and delta Y for a bunch of examples at the same time. And this allows us to do batch stochastic gradient descent. So instead of processing a single example, we can process a bunch of examples at the same time. So basically what we do is run a bunch of examples through the network, calculate the deltas for all of them, and then backpropagate those deltas through the network. And finally, we have to figure out how to update our weights in these networks. And the weight update rule is going to be another matrix operation, which is cool. And in doing our weight updates, basically remember that all we're going to do is take our sort of error or a delta at layer Y and multiply it by the input that was coming into that node from layer X. And so we have this matrix operation where we're taking our input X and multiplying it by our deltas at Y to figure out what our weight updates are for each of the individual weights in this matrix. Do sort of the matrix operations for doing forward propagation, backward propagation, and the weight updates make sense? Yeah. Good question. I sort of touch on it a little bit in the homework, but with gradient descent, you randomly initialize your weights, and you basically have a random model. It is good to have sort of some kind of smart weight initialization. So in the homework, basically, we use this heuristic where you're going to initialize the weights to be uniformly random between negative, I think it's square root of 2 divided by the number of inputs or something. But basically, there are a bunch of heuristics that people have come up with for like what this range should be of how big you should initialize these random weights to be. If you initialize the weights to be really small, it takes gradient descent a really long time to get anywhere because the output at every layer is going to be really close to 0, basically. If you initialize the weights to be really large, you're going to have model instability issues because the weight update rules, the amount of update that you're making to the weight is a function of basically what this input x was. And so as you're going through this network, if your weights are really large, x is going to have a really big magnitude at every layer. And so you're going to be making these really big changes to your weights. You're going to be like sort of driving the model all over the place and making these really big changes to it every round. So it's this fine line of basically trying to figure out what the right amount of random initialization should be. In theory, you can kind of initialize the weights to be any sort of random distribution, and you will eventually get to some kind of sensible answer if you do gradient descent for long enough with a small enough learning rate. But it could take a really long time, so we want to basically pick some roughly good random distribution to start with. Good question. Any other random questions about stuff? Cool. So we also talked about weight decay, which was our way of doing regularization on neural networks. So we talked about how neural networks are these really powerful models, and we need some way of reducing their variance. And one way that we do that with neural networks is basically limiting or penalizing really large weights in our network. So all we're going to do is basically take our loss function and add in this extra term, which is going to be the scaled value of the 2 norm of our weights w. So we have this lambda, which is this regularization parameter, and if we have a really high lambda, we're going to basically have really small w's everywhere, and it will be a really large penalty on these weights, and we'll get a lot less powerful model. If we have this smaller lambda, we will have sort of less penalty and be more prone to overfitting. So lambda is this new kind of knob that you can think about tuning and figuring out what the right values are. You could also imagine basically using things other than the 2 norm here to do regularization. L2 is just the most common one. And so this is called weight decay because when we take basically the the derivative of the L2 norm, what we end up doing is basically subtracting off a small amount of the weights at every round while we're doing our gradient update. And that small amount of the weights is basically going to be lambda times our learning rate, eta. We also talked about using momentum to speed up stochastic gradient descent. A lot of times we run into situations where it's really clear basically what direction the gradient is pointing, and we keep moving in the same direction over and over again. And if this happens, we basically want to start moving in that direction faster and faster. So we add in this new term to our update rule, where before we were basically just doing this update based on the derivative of the loss with respect to w. We're also going to add in a scaled component of how much we moved last time. So what this ends up doing is basically, if you keep moving in the same direction over and over again, it will speed up the direction or the amount that you're moving in that direction. You can think of this as basically like rolling a ball down a hill. The ball will kind of continue to gain speed until it gets to the bottom of that hill. And this also adds in sort of a smoothing component. So if you're making kind of a bunch of changes in different directions, this extra term will sort of start averaging out the changes that you're making to these weights. So instead of basically jumping around a bunch, you'll make a little bit slower but a little bit smoother updates to your weights W. Do people kind of understand weight decay and momentum? So our final update rules, after we added in these new components, we basically have our, instead of calculating the weights directly, the first thing that we're going to calculate at every time step is the change that we're going to make to the weights. And the change that we're going to make to the weights at time t is a function of basically the partial derivative with respect to our loss, but also this new weight decay term, and also a scaled amount of how much we change the weights in the last iteration. And then all we're going to do is basically add in a scaled amount of this change that we want to make to these w's to our current w's to get the w's at time t plus 1. And again, that eta is just our learning rate. We also talked a little bit about activation functions and the options that we have there in terms of what activation functions we use in the intermediate layers of a neural network. And so, we chat a little bit. We have this linear activation, which basically doesn't do anything, f of x equals x. We talked for a while about how that would be a bad idea to use basically everywhere in the neural network, because then our entire network would basically reduce to just a linear model. If our network is just a linear combination of linear combinations of linear combinations, the end result is just going to be one big linear combination of the input. And you haven't really done anything kind of extra. So what we really want is some nonlinearities to be sort of thrown into this network. And the most common ones when people first started using neural networks were the logistic function and the tanh function, mostly because they conform to the constraints imposed by the theorem that we saw that shows that neural networks are sort of arbitrary function approximators. So remember, with that theorem, the activation function was supposed to be bounded and monotonically increasing. So both of these functions are sort of bounded, logistic function. So the tanh is actually just a scaled and shifted version of the logistic function. But logistic is bounded at 0 and 1, and the tanh is bounded from -1 to +1. And both of them are monotonically increasing. And both of them also you can calculate the derivative for pretty easily. And a cool property of both of these activation functions is you can calculate the derivative f prime of x relative to f of x instead of relative to x itself. This is nice because when you're actually implementing these neural networks, you don't have to save around what the input was to an activation function in a layer, which can be sort of some extra information. Instead, you can just save what the output was from that layer. And then when you're trying to calculate f prime of x, you can do it just in relation to what f of x was. So in this case, for the logistic function, the derivative with respect to x of f of x is just f of x times 1 minus f of x. We have sort of a similar property with tanh. And you can also imagine that with our other activation functions, we have kind of the same thing going on. With the linear activation function, our derivative is just going to be 1 everywhere. But with our activation functions, logistic function and tanh, we have this property where they both are saturating. So we talked about this a little bit, but this is sort of a big problem in neural networks, where if you look at this derivative, when you get to sort of really large numbers, either below 0 or above 0, we have a derivative that falls off really quickly and basically becomes 0 in this component of the domain of this function. And what this means, if we have a really small derivative, is as we're backpropagating this error through the network, our gradients are going to be really small, and we're basically not going to update our weights at all. So if you have learning that's sort of taking place where all of your activation functions, the input to the activation, is sort of falling within this range, you're going to get kind of well-formed gradients, and everything's going to kind of work out nicely. But as soon as you get a bunch of gradients that are sort of in this, or a bunch of activations that are sort of in this range or in this range, you're going to have really small gradients, and your network is going to slow down in its learning a lot. And because these activations are sort of saturating, you run into these instability issues or these times when you'll be training a model and it'll basically stop learning, or it'll be really sensitive to sort of the initialization that you put for these weights. So instead of using these saturating activation functions, modern neural networks often use basically these non-saturating activation functions, either rectified linear units or leaky rectified linear units. So the rectified linear unit is very simple. We're just going to take our linear activation, but in the negative domain, we're just going to set it to be equal to 0. So f of x is going to just equal x when x is greater than 0, and f of x is going to be 0 if it's less than 0. We still have this nonlinear property, so we're not basically just training a linear model. We have this nonlinearity at this corner right here, where basically we have some positive slope here and we have some 0 slope here. This activation function is also like pretty much differentiable. We basically want our activation functions to always have some derivative that's easy to calculate. it's a little bit unclear basically what the derivative should be at this corner, but in practice we can just say that, if the input x is 0, we'll just say that the derivative is 0, and then if it's positive, the derivative is going to be 1, and if it's negative, it's going to be 0. Rectified linear units still have this saturating property, and sort of a more extreme version of it now, because if the input is negative, then the gradient is always going to be 0. And that means that if you have an activation, or if you have sort of a neuron in your network where the input is 0 for all of your data points, you're never going to learn anything with that neuron. It's basically going to be this useless neuron, because it's always going to output 0, and it's also never going to have any kind of gradient that goes backward through it, because the gradient through the activation function is always going to be 0. And that's when the weight initialization matters a lot, basically. If you kind of pick the correct weight initializations, or if you have a bias term and you make your bias be slightly positive, you can kind of ensure that all of your neurons will have some positive information flowing through them at some point. You have a question?
Is the choice of point 1?
Yeah. So then, if you're really worried about basically this saturation that happens in rectified linear units, you can move to these leaky rectified linear units. And this was just sort of an attempt to get rid of this saturating that happens in the negative domain. So we're still going to have this nonlinearity, but instead of setting f of x to be 0 when x is negative, we're just going to set it to be 0.1x. So we still have this nonlinear property, which is nice because our neural network isn't just a linear model. But now we have gradient basically everywhere. So if you have a neuron that basically is always kind of hanging out down here, it can slowly crawl its way back to maybe right here along this very small gradient that it'll get from this activation function. The choice of 0.1 is totally arbitrary, and you can think of using basically any constant here that isn't 1, and you'll get some good properties. Now, I don't think that the universal approximation theorem, so again, these are not bounded functions. These were bounded functions, so they fit into the constraints imposed by the universal approximation theorem. People have been working on updating the theory for these non-saturating activation functions, and I think there has been some progress, but I have to double check if they've actually proven basically the whole theorem for these non-saturating activation functions. But in practice, basically using one of these two activation functions actually works a lot better than using these saturating activation functions, because oftentimes, basically, the theory tells you just that things are possible, but it doesn't tell you the best way of doing those things. And in practice, there often ends up being sort of better heuristics that don't kind of perfectly match the assumptions that you're making with the theory. So in general, for this leaky activation function, you want that constant to be something that isn't 1, but there's a pretty wide range of things that people use. People have also done activation functions where you train in the neural network what that constant should be. You can imagine basically all we're doing with neural network training is taking these partial derivatives. You can actually calculate basically what the partial derivative of that constant should be at every time step, and then actually do some weight updates on that activation function as well. That kind of makes sense? Cool. And then we talked about basically we have so many hyperparameters. What are the right parameters to use? We've sort of, especially in computer vision, we've come up with a set of hyperparameters that everyone kind of uses for most of their models. These are very vision specific, but in general, they sort of give you good guidelines for what you want to start out at. In practice, especially this lambda here of 0.0005, this is what 90% of computer vision models use, but it's a very computer vision model specific parameter. So in practice, you'll probably want to investigate larger models or larger values of lambda if you're not doing a computer vision task. But typically, you'll find learning rates that are often sort of multiples of 10 from each other and are usually within some kind of range that looks like this. Momentum, I've seen people use, I guess, momentum of 0.5, but basically the only values that people use are 0.5 or 0.9. I've never found any reason to use anything other than 0.9. And for activation functions, relus or leaky relus seem to work basically as well as anything else that people have come up with. People have spent a lot of time trying to design new activation functions, and usually they get like maybe some tiny improvement on the data set they're looking at, and when you try to run those on other data sets, they don't really work at all. So just kind of stick to either relus or leaky relus. They work pretty well. So now we're going to talk about, what's that little bar on the side? I don't know. Convolutional neural networks, which are the exciting thing. Yeah? Yeah, so again, we have this property where with logistic or tanh, these saturated functions, you have very little gradient if the output of the function is sort of at 1 or 0, or if sort of the input to the activation function is above like, I can't really read that. Is that like, I think like once it gets past like 6 or 7, the input to the activation function, your gradient is really close to 0. And that means when you're backpropagating the error through this activation function, you're going to have basically very little gradient when you've done this backpropagation, because you're multiplying it by the derivative of this activation function. So your derivative is basically 0, and the weights that feed into a neuron that is saturated, is either like really high or really low, will basically not get any weight update as long as that neuron continues to be saturated. So you run into this situation where you have neurons that are saturated, that are either always really high or always really low in your network, and they're also not ever changing because the gradient that you're backpropagating through them is really, really small. So because of this sort of these saturation properties of these two functions, your network during training can kind of get stuck, or it can take a really long time to train because it takes a long time to basically push neurons out of this part of the activation function into a part of the activation function that has more meaningful gradients. So now we're going to talk about convolutional neural networks. And to start out with, we're just going to think about basically running neural networks on images. So neural networks are sort of these densely connected models where all of the neurons in one layer are connected to all of the neurons in the next layer. And so we can imagine for a second, Hog features. We talked about basically how neural networks are this combination of feature extraction and a linear model at the end. So we can imagine basically what the feature extraction part of a neural network might look like, and say that we wanted to extract something that looked sort of like Hog features. Hog features basically will take 8x8 patches and create sort of a 36 length feature vector for that 8x8 patch. So if we have some input that's 256 by 256, and maybe by 3 channels because it's an RGB image, and we want to extract something that looks sort of like Hog features, we're going to take 8x8 patches of this 256 by 256 image. So we'll get an image that is 32 by 32. And each of those 8x8 patches will have 36 features associated with them. So this feature image or feature map that we're trying to calculate is basically 32 by 32 by 36. And then imagine that we have a neural network where we're going from this input that's 256 by 256 by 3 to this feature map that's 32 by 32 by 6. It's going to be densely connected. So every input, every neuron in sort of this input is connected to every neuron in this hidden layer. And we're going to have 7.2 billion connections between just sort of our input and our hidden layer, which is kind of trying to imitate these Hog features. So already, basically, it seems like, OK, we want these neural networks to do some sort of feature extraction. But if we're trying to extract anything that looks like what our modern day features look like, it's going to involve just a huge amount of computation. And it's this huge amount of computation because images basically have a lot of pixels in them. They're really big. And neural networks are densely connected. So we have this property where basically we have O of n squared connections between these two layers, if n is sort of the number of neurons in each of those layers. But we don't really want this property when we're processing images. So you can imagine we have these two circles on this image. We have this red circle here and this blue circle here. And you can kind of think about the pixels in each of those two circles. They're really far apart, and basically they don't have much in common with each other. There's not really a lot of information that is shared between the pixels that sort of exist up here and the pixels that exist down here. So in images, we have this spatial information where basically nearby pixels have a lot of kind of shared information or have a lot of similarities with each other, whereas pixels that are far apart are kind of independent or unrelated to each other. And with this neural network, we're basically making this assumption that all of the pixels are related to all of the other pixels in some way. But what we really want is kind of some spatial constraint that says that nearby pixels are related to each other and far apart pixels basically aren't related to each other. So what we really want is kind of these sparse connections where we encode this property directly that nearby regions of an image are related and far apart regions of the image are not related. And if we impose this sort of sparsity, we have this model where basically we have connections between points in the image that are close by to each other. And we don't have any of these sort of long-range connections. So we don't have any connections from sort of this area of our input to any area of our input that is sort of spatially separated from that region. So the name sort of gives it away, but how can we sort of enforce this sparsity on our model? We just use convolutions. So remember that neural networks are basically taking a weighted sum of the input. And convolutions are also taking a weighted sum of the input, but just in smaller regions. So instead of taking, this neuron, for example, is a weighted sum of all of the neurons in the input. But with a convolution, we're going to say that every neuron is going to be a weighted sum over some image patch, but not basically all of the neurons in your input image. The extra thing that using convolutions does is introduce basically weight sharing into our model. So remember that when we're doing convolutions, we basically have this filter, and we run the same filter over all of the locations in an image. We're going to be doing the same thing in convolutional neural networks. So with our old model, basically, we see here that we have this model where all of these neurons are connected to all of these other neurons, and all of these weights are independent. So the weight that connects basically this neuron to this neuron is totally different than the weight that connects this neuron to this neuron, even though those two neurons are sort of have the same spatial relationship. Basically, they're directly across from each other. What we're going to do with convolutional neural networks is use convolutions to do this forward propagation. So in essence, we're going to be sharing these weights across different spatial locations. So if we think of basically this model on the right as being a rough approximation of a convolution operation, we have nearby weights related, or sort of nearby points of the image relating to each other, and we're also going to have this weight sharing where all of these weights that connect basically these points to these points are going to be the same as all of the weights that connect these points to these points, and the same as all of the other weights that sort of connect those two regions of the image together. And once we actually see how the convolutions work, this will make more sense. So we've added in these extra constraints to our model, where basically we started out with this model where we have these dense connections, and all of these weights are kind of independent of each other. And by introducing sparsity, what you can sort of think of it as doing is taking this dense model and setting a lot of the weights to be 0. So any of the weights that are connecting a pixel to another pixel where there's two pixels are really far apart from each other in sort of the input and output images, if they're really spatially far apart, we're just going to set that weight to be 0. And also what this convolution is doing is introducing this weight sharing constraint where if you have a weight that connects a pixel to another pixel, and those pixels have some spatial relationship, then if you shift sort of the neurons that you're looking at, say you look at the neuron that's 2 to the left and 1 up from that set of neurons. So the weights that sort of connect maybe this neuron to this neuron are going to be the same weights that connect sort of this neuron to this neuron. It's this weight sharing where the only thing that matters is sort of the spatial relationships between the 2 pixels because we're using this convolution operation. And because of this, we form a lot less connections. So instead of basically having n squared connections between these 2 layers, now we have O of n connections with this sparsity between the 2 layers. And we also have a lot fewer weights because we're doing this weight sharing operation. And so all of these weights will be the same as all of these weights, will be the same of all of these weights as all of these weights, et cetera. So we have a lot fewer weights that we have to remember and a lot fewer weights that we have to train. So convolutional neural networks are just using convolutions instead of these dense connections to process images. And the important part of these networks is basically we're taking advantage of the structure in our data. We're taking advantage of this thing that we know about images that holds true, which is that basically nearby pixels are related and far apart pixels aren't related. So we're imposing basically this additional assumption on our model. Who can tell me, in terms of this concept of bias variance, what is this constraint, or what are convolutional neural networks doing to the bias and variance of our model relative to sort of our original formulation of neural networks? Anyone? Someone knows. Yeah. Yep. And what does that do to variance? Huh? Exactly. So what we're doing is basically shifting the bias and variance of our model. So we're imposing this additional bias on our model. And imposing this bias is going to decrease our variance. But the really important thing here is that the increase in bias won't hurt us very much. And we can sort of think of this as, we have this really powerful model, but we don't actually need it for images. The only sort of thing that we need for images is these convolution operations because we know this information about how pixels are related to each other. So for example, when we were talking about basically fitting lines or fitting curves, we had that example of the data points that a parabola could fit really well. And you could imagine that all you need for that is basically a model that takes into account x and x squared to fit a model to that data. And if you had some really high dimensional polynomial that you were trying to fit to that data, you'd get a pretty good fit, but it might be harder to figure out what all of the weights are for that high dimensional polynomial, when really all you need is just a model that is quadratic. So reducing the bias, or increasing the bias, and going from a model that's some really high dimensional polynomial to just a quadratic model doesn't actually affect the end fit that you're going to get for that data, but it does greatly reduce the variance of your model. And that's sort of what we're doing here. So we are increasing the bias of our model and decreasing the variance. But in this case, having the extra bias didn't actually help us because we were just sort of introducing a bunch of complexity to our model that we didn't actually need. And that's what's cool about convolutional neural networks. We're basically using this structure to get a much simpler model that's easier to train, but will actually function better than using just neural networks in general because so this convolutional network will function better than just using these fully connected models because we've decreased our variance and we've increased our bias, but the increase in bias basically doesn't matter very much for fitting this function. So now we're basically going to have a bunch of these new, let me just try to get rid of this thing. We have a bunch of these layers that we're going to talk about when we're talking about convolutional neural networks. So the simplest one is just this convolutional layer. So the input to a convolutional layer will be an image. And the way that we process this is just with convolutions of multiple filters. So our image will have some width and height dimensions, and it'll also have some number of channels. And we will have basically a filter bank at every layer. and we'll run that filter bank over the input image to produce some output image. And before, we've usually run basically 1 or 2 filters at a time. As we start talking about these convolutional layers, we'll have a lot of filters that we're going to be running on the same feature map. And one thing you can kind of think about is like, if you want to detect, for example, oriented edges in an image, one thing you could do is basically run filters that detect basically horizontal lines and vertical lines, and then lines at a bunch of different angles. And each of those convolutions would be sort of a separate filter. So our convolutional layer will have a bunch of filters, and we'll run it over our input image, and we'll output some image that has some number of channels. And each of those channels will basically be the response map of one of the filters that we have in our convolutional layer. So again, we have this property where the output is still just this weighted sum of the input, and we'll probably apply some activation function to it. But to calculate the weighted sum, we're just going to use the convolution operation instead of using this big, dense connections that we have between 2 layers. And we have a bunch of parameters that we can, yeah. Oftentimes, the filters will sort of learn different things because gradient descent will kind of push them to be different. If you already have a horizontal edge detector, you don't really need another one. So it will be beneficial to the model to push a bunch of filters to start specializing and doing different things. You will often have filters that look sort of similar that are kind of doing related things. But in general, you will get kind of some diversity in your filters without even adding in sort of any additional constraints that your filters, for example, should be diverse. Yeah, so oftentimes, yeah, you do have to kind of resize these images so that they're all the same size, or often you resize them so they're all the same size when you feed them into the neural network. You do get weird things that happen if you have really big changes in size. So if you, for example, have trained on images that are all about the same size, and then you start feeding in examples where you've like zoomed really far in, the things that you were looking for before have changed scale a lot, and your model will start to break down a little bit. So for example, if you were looking at faces and all of the faces were like 32 by 32 pixels before, and then you want to look for faces, but the faces are going to be like a lot larger, like 512 by 512 pixels, the edges that you were looking for and sort of the features that you were looking for are going to change, and you'll have to basically do some retraining. The filters in general will be at a good sort of starting point, but they probably won't work well across like a wide variety of changes in terms of like scale of the image and stuff. So often the way that you deal with that is you train these networks with a lot of data augmentation. So you, while you're training them, will basically do a bunch of resizing and cropping to your image so that the network is used to looking at images of different scales and with different sort of properties. Question. So we have a bunch of things that we can think about when we're coming up with these convolutional neural networks. One important parameter is kernel size. So this is just how big the filter is for a given layer. So a lot of times in the past, we've looked at filters that were like 3 by 3 or 5 by 5. In general, that is about sort of the order of magnitude that you expect for filters when you're processing images. Again, if we made these filters like really big, we're just going to end up with sort of a densely connected network again, and that's not really what we want. We want some sort of locality constraints. So in general, people sort of use filters that are like 1 by 1 to about 11 by 11. The most common one is probably 3 by 3. So in general, people nowadays just kind of build networks that are like 3 by 3 convolutions and 1 by 1 convolutions, and that's it. And these 1 by 1 convolutions are a little weird. All a 1 by 1 convolution is the output is going to be a linear combination of channels in the previous image. So you have one pixel location in your input, and you're going to do some linear combination of the channels in that pixel, and that's going to be one pixel and one channel in your output. and you lose basically all of the spatial processing, or you're not really taking into account any spatial information. So people often use basically 3x3 filters to do some spatial processing, and then they use 1x1 filters to do some kind of extra processing that doesn't really need to take into account spatial information. So again, we're going to have some number of filters, and we're talking about sort of kernel size in terms of the spatial dimensions of the kernel. Filters also have some number of channels, and usually the number of channels is just going to be the same as the number of channels in the input image. So every kernel is going to be a weighted sum across some spatial dimension in the input image, but also across all of the channels. We also think about when we're doing convolutions, another thing we can think about is basically whether or not we're going to use padding and how much padding we might want to use. So we ran into this before, where basically convolutions, especially if you have sort of really large convolutions, will start running off of the edges of your image. So if we have some image down here, I think this is 8x8, and we run a 3x3 filter on it, and we don't sort of introduce any padding, if we're just running the filter so that all of the input pixels in the filter are in the actual image, then basically our output from running that filter is going to be a smaller version of this input image. We're going to have basically we're going to cut off basically some of the pixels along the edges, because the first sort of pixel that we can run or apply this filter on is this pixel right here, instead of running it on this pixel, because that would mean that some of the filter basically fell off the edge of the image. So if we don't have any padding, we basically run this 3x3 image, or run this 3x3 kernel on this 8x8 image, and our output will be this 6x6 image. The thing that we can do to kind of correct this is add in some padding to the image, and you guys sort of did this implicitly by implementing your convolutions in terms of getPixel, which does this padding automatically. But we can imagine basically adding in sort of an extra border around the input image, and by doing that, our output image will have the same dimensions as our input image. Padding can also be a lot larger, so you could imagine that if you added in more pixels to the outside of this image, the output image would actually be larger than the input image that you sort of fed into a convolutional layer. The type of padding that people use also will play some role, although it seems like it doesn't make a ton of difference in terms of what the end sort of output is of the model once you've kind of trained it all. The most common thing that people do is just zero pad their images, because again, when you think about basically what these neural networks are doing, a lot of times the intermediate layers are doing some kind of feature calculation, and those feature calculations are usually really specific to that location in the image. So if you do any of the other padding where you take pixels from inside the image to put for this padded region, you might be basically adding in some kind of information to the image that isn't actually true, or isn't actually what's going on in the image. So kind of the safest thing to do is just set the border, this sort of added in pixel region, to all be 0. And your network kind of learns over time that there isn't a lot going on the border, and there's also not a lot of information that you can kind of get from this padded region, and that it should concentrate, most of the information is coming from the interior of this region where there's actually, interesting stuff happening. Does this notion of sort of padding make sense? You guys have run into this before, so.
What would be the benefit
I don't know, but I've seen people do it. I can't remember why they did it. It's a good question. And again, there's a lot of different options for a lot of these things, but there's also sort of a bunch of set things that people normally do. So normally people are going to use 3x3 convolutions, and normally they're going to add 1 pixel of padding, because that's just kind of the right amount to make it be the same size as your input and output. But in the past, when people first started training these things, they didn't use padding, and they did actually have this sort of slow shrinking of the output feature map after every layer, which means that you can't have very many feature maps, because eventually your image is just going to disappear. The last thing we can think about is striding. And this is how far to move your filter between applications. So in the past, basically, we've always done convolutions using a stride of 1. So we applied the filter, and then we moved it over by 1 pixel, and then applied the filter, and then moved it over by 1 pixel. But in practice, basically, we don't have to do that. We can move the filter sort of arbitrary amounts. So people often will stick to sort of strides of 1, or sometimes strides of 2. So you can imagine that basically a stride of 1 will keep the approximate image dimensions about the same, especially if you use padding, then a stride of 1 will basically give you the exact same dimensions in your output as in your input. But if you used, for example, a stride of 2, you would get an output image that is downsampled by a factor of 2, because you're only applying the filter basically to half of the locations that you could have applied it to. Or not even half, a quarter, I think, right? But in every row, you're only applying it to half of the pixels, and you're only applying it to half of the rows, because you'll sort of move it over by 2 and over by 2, and then when you go back to the beginning, you'll move it down by 2 pixels as well. So people use striding in some cases to sort of do this downsampling of the images. And again, we're going to basically implement all of these using matrices, because actually implementing convolutions, as you guys probably saw in your homework, is complex. And it's also hard to basically get it to be really efficient. Whereas we know that in practice, we have a bunch of algorithms. So basically, a bunch of people have spent a lot of time making matrix operations really efficient. So any time in machine learning, or just sort of in computer science, when we want things to be really efficient, if we can turn those problems into matrix operations, we basically know that we'll have a really efficient implementation, because matrix operations are really fast. So we have to figure out basically how to turn these convolutions into matrix operations. And the key idea is this im to call method, or sort of this im to call idea, where we're going to be taking spatial regions of our image, or spatial blocks, and putting them into the columns of a matrix. So what we're seeing in this little example is basically taking 3 by 3 regions of the image and taking those pixel values to fill in this matrix, which will sort of encode all of the pixels in the image. But in particular, it'll also have basically some duplicate information. So for example, we have this pixel right here, which falls into a few of these different regions when we're basically sliding this 3 by 3 window over the image. So this pixel here will show up basically as the center pixel in this green column. It's also going to show up as this pixel in the blue column as well. So I think probably like that pixel in the blue column, or one of the pixels in the blue column, et cetera. So we are duplicating some information when we're using im to call. But in general, we're sort of basically doing some setup. So we're rearranging how we're storing this image. And in doing so, it's going to make these matrix operations possible. And it's also going to make sort of the memory access really efficient when we're doing the matrix operations. So the first thing is we basically use im to call to rearrange this image. And obviously, we have images that have multiple channels. So what we're going to do is basically stack those channels on top of each other in this large im to call matrix. So again, each of these columns is associated with just some small region of our image. And if we think about basically the rows, we're going to be going over different spatial locations in terms of one application of the filter. And then once we get far enough down, we're going to be going over the same spatial locations, but just at the next channel and at the channel after that, et cetera. And now we have basically this new representation of our image. And what we could do is just multiply it by our filter bank to perform our convolutions. So we have a bunch of filters. And again, we talked about how the filters have basically some size. So they have some kernel size. And for example, a filter might be 3 by 3. And the filters also have to have some number of channels. And the number of channels is going to be the same as the number of channels of the input image. So if we have these filters and we have them arranged in a matrix as well, we can imagine that basically every row in this filter matrix is a separate filter, and every column corresponds to basically a row in this im2col matrix, or every row in our filter matrix is some spatial location. So the top row is sort of the top left of the filter. The second row is maybe the top middle. The third row is maybe the top right of the filter, etc. Once we loop over all of the spatial locations, we'll go to the next channel of the filter, and we'll loop over all of the spatial locations again, and then we'll go to the next channel, etc. And there are some number of filters, which is, sorry, I think I might have gotten my, sorry, I was explaining that wrong. The number of columns, so the number of rows is the number of filters, and the number of columns is associated with the spatial location of every filter, and then the number of channels of the filter. So we have our filters stored in this matrix, and now all we have to do to basically apply this convolution operation is multiply our filters by this im2col matrix that we created. And you can sort of convince yourself that this works just by looking at the dimensions of the matrix. So our filters basically have some number of filters of rows, and they have some size, which is the size of the filters. So in this case, it might be 3 by 3 by the number of channels. And our im2col matrix has a bunch of spatial locations. So this is all of the locations that we want to apply the filter. And it has some number of rows, which also corresponds to basically the size of the filters that we're going to be applying. And when we do this matrix operation, we end up with this output. And the output is the number of filters in terms of rows, and the number of spatial locations that you applied those filters in terms of number of columns. And what this ends up being is actually just a direct representation in channel height width format of our image. So remember we talked about how basically the number of filters is going to be the number of channels in the output image, and the spatial locations, when we sort of did this im2col function, we arranged the im2col matrix in terms of rows first, and then subsequent, or sort of in terms of columns first, and then in terms of subsequent rows of our input image. So our output image actually just ends up being basically a direct application of this convolutional filter bank on top of the input image. Do people sort of believe me a little bit that basically running this matrix math corresponds to applying a bunch of filters onto an image and figuring out, again, just remember that applying a convolutional filter is just doing a weighted sum of the input at a bunch of different locations, and all that matrix operations are is doing a weighted sum of two different things. And in this case, we have our convolutional filters, and we have some representation of our image where we basically already extracted what the different regions are where we're going to be applying these filters. Yeah?
So that means
yes, exactly. Don't do that. Yeah, that's a great point. In these convolutional layers, all of the filters are going to be the same size. And if you want to basically have a layer where you're applying a bunch of different sizes of filters, you can't do it. So one thing you can do instead is have a couple different layers that take input from the same place and use different size filters. So this is something that Google does a lot, where they want to run on the same input image. They want to run some 3 by 3 filters, some 5 by 5 filters, and some 1 by 1 filters. And they'll have 3 different layers to do each of those operations. So you can't basically do it as a single layer, but you can do it in terms of multiple layers. And then each of those layers is going to produce some feature map. And those feature maps are going to be the same height and width dimensions. They'll have maybe a different number of channels if you have a different number of filters, but they'll have the same spatial dimensions. And so then you can take all of those output feature maps and just stack them on top of each other. And that can be the output of a combination of those three convolutional layers. Yeah. I guess that's another option. Basically, if you wanted to have one layer that used 1 by 1 and 3 by 3 and 5 by 5 filters, you could have just one big layer that does all 5 by 5 filters, but a bunch of the 5 by 5 filters have zeros in most of the places. But in practice, running 5 by 5 filters is pretty computationally expensive, especially if the only thing you care about is like a 1 by 1 convolution. So people tend to actually break it up into separate layers. But I think also you would have to impose the constraint manually that you wanted the filters that sort of started out as 1 by 1 or 3 by 3 filters to stay 1 by 1 and 3 by 3. Because otherwise, as you're doing gradient descent, those filters might start out with a bunch of zeros in them, but over time they would change, and those zeros would become positive or negative components, depending on whatever was useful for the network. But the biggest thing is just efficiency. It's way more efficient to do 3 by 3 or 1 by 1 convolutions than 5 by 5 or 7 by 7 or larger convolutions. So this is kind of the forward pass when we basically want to take some input feature map and produce some output from our convolutional layer. We also want to be doing gradient descent using these convolutional layers. So remember that before we basically, to figure out how much we wanted to change the weights, we would take some notion of error or delta at the output of a layer, and we would multiply it by the input of that layer to figure out how we change the weights. We're going to be doing basically the same process using convolutions and matrix operations, again with our im_decay. So if we have some delta or some error that basically we want to correct in our layer, and we want to figure out how much to change our filters by, we can still form this as basically this matrix operation where we have some delta which corresponds to basically the same size as the output of our image. So we have some number of filters and some number of spatial locations. And this is the size of basically the output of our convolutional layer. And we're going to take basically the same im_decay, but we're just going to transpose it. And when we do this matrix operation, we basically end up with a matrix that is the same size as the number of filters, or it's the same size as the filter matrix that we had before. And you can sort of work out on your own basically what this corresponds to if we take this delta and multiply it by the transpose of this im_decay matrix. But basically, we're doing the same operation that we were doing before, where we have some delta, and we want to multiply that delta by the input that went through some weight, and that will get the amount that we update that weight by. I don't think so, but I don't know exactly. The way that people normally implement it is just sort of looping over the image and manually building up this matrix from scratch. So you're just sort of looping over all of the spatial locations that you're going to be applying a convolutional filter and taking out all of these pixel values and basically just stacking them together. And it doesn't sort of strike me as something that can be matrix operation because you have sort of this weird duplication that's happening, but you also have like a lot of things that aren't. I would have to think about it a little bit, but I'm pretty sure. I mean, maybe you could if you have like a really big matrix that you're multiplying it by, but at that point you're losing some of the efficiency that you kind of want. So we have some method of basically taking this column matrix representation of our image and calculating the updates to our filters. Again, remember that we're also doing this weight sharing thing where basically the same filter is going to map, or is going to be sort of the weights that connect some input pixels to some output pixels are going to be the same across a bunch of different locations. And this is kind of represented in how we're doing this weight update here, where the weight updates for a specific weight in our filter bank are actually going to be a sum of a bunch of different multiplications that are happening. So when we just had a weight connect a single input and a single output, all we did to calculate that weight update for that one weight was take the delta of that neuron and multiply it by the input to that weight. But now we have basically the same weight being used across a bunch of different locations. So we have to sum up across all of the locations where we use that weight, what was the input to that weight, and what was the error produced by that weight. And that's what we're doing basically with this matrix operation. We're summing across a bunch of different locations what the input was to each of these weights and what the delta associated with the output of that weight is. And now we have one final component that we have to do, which is backpropagate the error to the previous layer. And again, we can use sort of these matrix operations to perform this. And remember that when we're doing this backpropagation, all that matters is sort of the error that we have at our output, and we're backpropagating it through our filters. And so again, we're going to have this matrix operation that happens where we're taking these filters and basically doing the inverse of a convolution operation. And we end up with some representation of our input image in terms of the delta associated with that input image. But in this case, we're doing basically the inverse of a convolution. So we're taking our filters and our gradient information and backpropagating the gradient, or backpropagating the delta through the filters. And so we're going to end up with some matrix that looks like the input that we passed into this layer to do forward propagation. It's going to have this property where it is sort of the result of running im to call on some actual image. So we just have to take this output matrix and do the reverse operation of im to call to basically map backward from this column matrix that encodes some image information to what that actual image would have been. And this is going to involve, again, summing basically. So remember that when we were doing this, we have this pixel in the image is going to show up in a bunch of different locations in this output matrix that results from calling im to call. And when we do sort of this inverse operation, we're basically going to have to sum the delta information across a few different places in this matrix that all correspond to basically the same pixel in our image. And this will calculate basically the delta or the error associated with that image. So this is cool. We have these convolutional layers, and we can implement them in terms of matrix operations, which is always nice for efficiency. But images are still really big. And so if we have maybe a 256 by 256 image, we have a bunch of pixels. And this is still sort of considered a small image. So you can imagine that basically running a convolution operation or running a convolutional layer on this image will output basically a bunch of different feature maps. And now that we've run this convolution operation, maybe we can start basically getting rid of some of this pixel information. So once you've detected, for example, horizontal lines, you know that if there's a horizontal line in one location and you move a little bit to the left or right, there's still going to be a horizontal line there. That's sort of the whole point of doing line detection. So we can basically start doing some subsampling after we've performed some of these convolutional operations. And the idea is basically, you guys implemented this before. Basically, often what we want is when we're looking at a feature map, we want to figure out what sort of the largest responses are, or we want to get some general idea of what's going on in our feature map without actually having every specific pixel kind of matter in terms of what we're looking at. So we're going to start aggregating some of this information and doing some subsampling. And to do that, we're going to use pooling layers. And so the input to a pooling layer is still going to be an image or a feature map. So remember, for all of the components of convolutional neural networks, our input is usually basically something that looks like an image. It has some sort of width and height, and it has some number of channels. It might be an actual like RGB image, or it might be the output of a previous convolutional layer that is just some feature map that has some spatial dimensions and some number of channels. And a pooling layer is basically going to pool pixel values over some region and output a smaller version of the input feature map by a factor of some stride. And so the stride, again, is similar to the stride that we talked about when doing convolutions. And one way that you can imagine doing downsampling in a convolutional network is by using strided convolutions. Another way that you could do it is using these pooling layers. So there are a bunch of, again, different ways that we can implement pooling. You can think about basically different kinds of pooling. So you can do average pooling, which means that we would just look at sort of a local region in an image and average together all of the pixel responses. You could also do average and mean are obviously the same here, but you can imagine doing like median pooling instead of mean pooling, or max or min pooling. You also have to pick basically a stride for how often you're going to be applying this pooling operation, or how far you're going to basically walk before you look at the next local region of pixels. And your stride is going to control how much you're downsampling the image when you apply this pooling layer. And you also have to think about how big of a region you want to look in. And sort of the most common hyperparameters when we're talking about pooling, you're usually going to be doing a max pooling operation. And you're usually going to be using a region of about 2 by 2 or 3 by 3. And often you're going to use a stride of 2 so that you downsample the image by a factor of 2. This is just sort of the most common, and people use other versions of this, but this is often what you'll see in practice. So just a really simple example, if we have a max pooling layer and we're going to look at 2 by 2 regions and we're going to use a stride of 2, the first thing that we'll do is sort of look at the top left of this image and we say, okay, here's a 2 by 2 region in the image. What's the largest number in this? And it's 6. So we take 6 and we put it into the corresponding pixel in our output image. And then we move the filter over by 2 pixels. So again, we have this 2 by 2 region. We're going to figure out what the maximum value is there. It's 7. And we're just going to keep doing this operation across the entire image. And again, every time we sort of do this pooling operation, we're going to move the region that we're looking at by a factor of 2 pixels. And then when we get to the next, when we sort of get to the end of this, we're going to move downward by 2 pixels as we start looking at the next row. And we just sort of fill in the entire output from our input. And we have basically the largest filter responses for a region. And you can sort of think of this a little bit like doing some feature processing. It's kind of similar to like the non-max suppression that you guys were doing. So remember that like if we're looking for like lines or edges or something in some region, oftentimes all we care about is basically like what is the largest response that we have in a region. We don't necessarily need to know that all of the pixels in a region were associated with some horizontal edge. We might want to know if just like somewhere in that region is a horizontal edge or a vertical edge, et cetera. And so that's what this max pooling operation is doing, is just sort of aggregating feature responses over some area. Did you have a question? So the last thing after pooling operations is these fully connected layers. And these are just sort of the normal neural network layers that you guys are super used to. So every neuron in the input to this layer is going to have some weight connecting it to every output neuron. And often fully connected or connected layers are used in convolutional neural networks to basically go from the output image feature map that you have after doing a bunch of convolution operations to what your actual predictions are. So at some point you have to make some predictions. You have to output some vector, maybe like a 10-dimensional vector or something. And you will often use sort of a connected layer for doing that. So these are sort of all of the building blocks for convolutional networks. We have convolutional layers, pooling layers, and connected layers. We'll talk about in the future some more advanced layers that people use for special tasks. But in general, these are just kind of like most of what you need to implement modern convolutional neural networks. And next time, we'll talk about what we will use these things for. See you guys later.